In this lecture, we're going to look at logic gates, the most basic building blocks of the digital computer. We're going to use this opportunity to teach how functions are defined in Shen and how we can define logic gates. And in the next lecture, we can use a technique called information hiding to construct more complex logic circuits. Now, in computing, a logic gate is a device that receives signals and transmits a signal. A signal is either low or high voltage, and conventionally a low signal is represented by 0 and a high signal by 1. An AND gate is a gate that receives two signals and outputs 1 just when both inputs are 1 and 0 in all other cases. This is often represented as a table like this. The symbol for an AND gate is shown alongside the table. In Shen, we can represent this table as a function AND gate defined as follows. We could see that the transcription of the table into Shen is very simple and direct. Let's try this out. If we want to activate the type checker, we have to add the type to this function. Our type says that an AND gate receives two inputs, which are numbers, and outputs a number. Let's note that our function is not defined for all numbers. If we enter an input other than 0 or 1, we get an error. AND gate is a partial function. It is not defined for all of its possible inputs. Our function returns 1 just when both inputs are 1. If both inputs are not 1, Shen will still try the other rules even though, supposing that the inputs are binary, the result is determined. An alternative would be to say that if the inputs are not 1, then 0 should be returned whatever the inputs. We could say that if inputs x and y are not 1, then the result is 0. X and y are variables. They stand for any input you like, and in Shen, a variable is a symbol beginning with an uppercase letter. Let's notice two things here. This definition works because Shen tries the rules in order. If we were to swap the order of the rules and place the second first, then the function would always return 0. The other rule would be totally redundant and would be starved by the first rule. Second, our new function is a total function. AND gate now accepts all inputs and returns a response. If we turn off the type checker, we can even type strings as inputs. However, with respect to binary numbers, the new definition is observationally equivalent to the old. Notice that the variables in this definition are not used in the output. A variable that occurs once in a rule and is therefore not used in the output is called a singleton variable. We can mark the occurrence of singleton variables by wildcards or anonymous variables which in Shen are marked by underscores. Using wildcards enables people reading your code to quickly see when a variable is actually not used in constructing the output. Now a word on loading these programs. You can see that for pedagogic reasons I am pasting these programs into the REPL. But actually programmers do not work like that, but instead create a file and load the program into the REPL using the command load. What follows the word load is a path name, and a path name is a string that gives the location of the file. In SBL Shen used here, you could drag the file into the window and the relevant path will appear. Creating a program file generally means using an editor of which there are many, but you need to know that this editor has to produce readable code. An editor like Windows, like Word for example, will produce an output which is not readable to Shen. If you're using Windows, then Notepad is an entry-level editor which will do the job. Consider though downloading Notepad 2 or Notepad++, which have greater capability. I'll assume that you know how to create and edit files in this lecture series. Another form of gate is an OR gate whose table and symbol looks like this. And in longhand, the corresponding Shen function looks like this. Or in our shorthand version, like this. Notice we've put a comment in this code. Finally, an inverter has this table and definition. For constructing logic circuits, computer technology uses two basic components, NOR and NAND gates, for which the gates we've discussed can be defined. The table and symbol for a NAND gate looks like this. As you can see, a NAND gate returns 1 in all cases, except where the inputs are both 1. A NAND gate is an inversion of an AND gate, and hence the term NAND, short for not AND gate. The longhand definition is, and the shorthand is this. The utility of NAND gates is that they can be used to define other gates. For example, we can define an inverter by splitting a signal down 2 wires to a NAND gate. If we assume that splitting the signal does not cause the signal to deviate from high when it is high or low when it is low, then the effect is to create an inverter. If the input is 1 high, then the NAND gate will receive 2 1s and output a 0. If the input is 0, then the NAND gate will receive 2 zeros and output a 1. This is precisely what an inverter does. If we want to define this in Shen, then we use a variable x in which the input x is repeated to the NAND gate function. Now let's define an AND gate. An AND gate is a result of feeding a NAND gate through an inverter. The result of negating a NAND gate gets you to an AND gate. An OR gate is the result of feeding both inputs through an inverter and submitting the inverted results to an AND gate. In logic circuits, you'll often see more than two inputs feeding into an AND gate or an OR gate. These are called multiple input gates, and we can build them from basic AND and OR gates like this. Instead of taking a NAND gate as basic, we can instead base our designs on NOR gates, which have this table. An inverter is created by passing the same input down both channels to a NOR gate. And not surprisingly, we can create an OR gate by passing a NOR gate through an inverter. And finally, an AND gate is created by passing both inputs through inverters and passing the result to an OR gate. Before we close this video, it is worth noting that Shen already has something similar to the AND gate and OR gate functions. The function AND works very much like AND gate, except it uses true instead of 1 and false instead of 0. Similarly, OR does the job of OR gates with booleans instead of 0 and 1. And lastly, NOT mimics invert over booleans. Just as AND and OR gates can be defined in terms of the more fundamental NAND gate, these boolean operations can be defined in terms of the if of Shen. If takes three inputs, and if the first evaluates to true, it returns the result of evaluating the second, and if the first evaluates to false, it returns the result of evaluating the last. So AND PQ is just if PQ else false, and OR PQ is just if P then true else Q, and NOT P is just if P then false else true. One point to note here, by the way, is that the method of evaluation for these Boolean operations is slightly different from the method of evaluation which is used throughout Shen. If I submit two inputs to the AND function and the first one evaluates to false, then there's no point looking at the second to see what the result should be. This is called non-strict evaluation. That's to say, the inputs to the function are not all evaluated before the function is applied, which is generally the result which is expected of all other cases in Shen. We could see this if we turn off the type checker and submit to the AND function an input whose first argument evaluates to false and whose second would normally raise a type error. The fact that we get false back shows us that the second input is never evaluated. Well, that's all for now. You can get these programs from the following address. In the next video, we'll see how to combine logic gates together to make a logic circuit that does something useful. Do subscribe as I produce more Shen videos, and keep our work going by donation to the Shen project using the donations page link. I do hope you've enjoyed this presentation.